Okay, so before we start, can you guys just give a brief introduction about yourself, like your name, what year of program are you currently in, and like where are you from?
Hi bro, I am Pragadishwar Babu from Nagarkoil.
Nagarkoil, okay. And
Bro,
what?
I am
Yeah,
Mahendran bros. I'm intern there.
okay,
Last one.
nice. Are you doing BTech Chemical Engineering?
Yeah bro.
Uh,
BTech
what year are you currently in?
final year.
Final year, okay, good. Um, who's the other person? Ritu Rani.
Hello.
Hello.
Yes, sir. Currently, I'm doing job in JK Cement, and I have completed my BTech in Chemical Engineering this year only.
Okay, nice. Okay, fine. Let's start the today's session. So I am guessing like you guys must have learned mass transfer, right? Mass transfer and mainly distillation in your BTech curriculum. And since like Ritu has completed, I think she must have completed that course as well. And Pragadesh,
Sorry, sir. I'm hello.
am I audible?
Yes, sir. Right now, you're audible.
Okay. So like I was asking like if both of you guys have done the mass transfer course during your curriculum, like are you well versed with mass transfer and so on? So mainly distillation. So like today's class will be with respect to distillation and some of the questions which were asked in previous year gate from the distillation part of mass transfer. So we'll be looking into distillation. Fine. Let's So, like, how do you guys want me to like proceed? Like, you want me to like give a brief introduction to distillation, like the McCabe-Thiele method and so on, or shall we just straight away go into the questions because you guys have learned these concepts in your classes?
Sir, give some introductions.
Okay, fine, sounds good.
Thank you, sir.
Okay, so let me just get the. Okay, I hope my screen is visible to you guys. Slideshow.
Yes, sir.
Okay. Fine. So today we'll be learning about distillation. So distillation by definition it is nothing but a separation process. Sorry, separation process and this separation occurs based on the various different properties. Like can you name a few properties by which distillation occurs in normal process? Like just take a guess, that is fine. Okay. So distillation mainly occurs based on the difference in the boiling points. boiling points of components in a mixture. Okay, more people have joined. Fine. Yeah. So distillation occurs based on the difference in the boiling points of the different components in a mixture. You can also say it is due to the vapor pressure, the difference in vapor pressure of these components, or you can have another term called as relative volatility. So this relative volatility is just a measure of how volatile a component is with respect to another component. So for example, if we want to find the relative volatility between components 1 and 2, we can represent the relative volatility of these components as alpha 1 2, and by definition the relative volatility, we can find this relative volatility of 1 as y1 by x1 by y2 by x2. So this y1 y2 are the vapor mole fractions of component 1 and 2, and x1 x2 is the liquid mole fraction of component 1 and 2. So in this formula, it is important to note that the component 1 is considered more volatile than the component 2. So usually relative volatility is you know greater than or equal to 1 in most cases. Fine. So yeah, this is just the basic concept of distillation. Now in when it comes to gate and gate syllabus, there are only a few topics which are like really stressed important for gate. So let's get into that. So okay, fine. Now we have learned relative volatility. What else? When we design a distillation column, so we can represent a distillation column like this. So we have the feed here, we have a condenser unit from which distillate comes out, and then we have a reboiler unit from which the residue comes out. So feed is usually represented as F and its composition as XF. Then distillate is represented as D, composition XD, and the residue is usually represented as W, or in some cases you can even see it represented as B or R. So here we'll just go with W and the composition as XW. Okay, so in a distillation column there are a lot of trays inside the columns. So there are different types of trays that you can find: bubble cap, and like so on. So what these trays do, the mass transfer occurs, or the separation in the distillation occurs, the mass transfer occurs within these trays. So like in normal application, we usually want to find how many number of trays are required for a given distillation process. So this is one of the most sought out problems in distillation part of mass transfer, and it is also important when it comes to gate. So we can find this number of trays using various methods. The most famous method is called the McCabe-Thiele method. Then there is a second method called Ponson-Savret. Ponchon-Savret, and then there are a lot of formulas, mainly Fenske's equation. And there are a lot of different types of a Fenske's equation as well. You have something called as a Fensky-Underwood equation, and so on. So these three are the main, ways by which we can calculate the number of trays in a distillation column. Okay, 1 second. Okay. Oh, fine. Now let's get back to our distillation column. So we had the feed F, the condenser on top, which gives us our distillate D, and the reboiler on the bottom, which gives us our residue W. And their corresponding compositions are XF, XD, and XW. Okay. So I hope you guys know how to write a mass balance for simple systems. Like you must have learned it in process calculations as well. So can anyone like just say how we can write a simple mass balance of this distillation column? Okay, fine. So a simple mass balance of the distillation column, you can write it as F is equal to D plus W. So whatever comes in goes out. So feed is what is coming inside the distillation column, and D and W, the distillate and the residue, are what goes out of the column. Now we can write a component balance. Now this component balance is written for the more volatile component. Now when we say XF, XD and XW, these mole fractions actually represents the mole fractions of the more volatile component. So if we want to write a component balance in a distillation column, it is nothing but FXF is equal to DXD plus WXW. So this is a component balance. So you can write a similar balance for both the condenser as well as the reboiler as well. So like let's say, yeah. So when we write, okay, 1 second. Yeah. Yeah, sorry about that. Okay. So let's say in a condenser, now this top part is, let's say, the condenser part. So there is a vapor V that is going into the condenser. Then there is a fraction of this which is liquid usually, which goes back into the distillation column, and D is the distillate. So when we write a condenser balance, it is V is equal to L plus D, and similarly we can write a reboiler balance as well. So let's say L dash and this is B dash. So reboiler balance will be L dash is equal to V dash plus W. So these are just simple mass balance equations throughout the distillation column, right? So let's look into the few basic assumptions of McCabe-Thiele method. So can anyone say what are the different assumptions or some of the assumptions associated with McCabe-Thiele method? Anyone? Okay. So some of the assumptions, let's say, so there are no heat loss or heat gain occurring in the distillation column. That is, it is basically an adiabatic operation. Then the another assumption is that there is no heat of mixing. And then the most important assumption is constant molar heat of vaporization. So what this essentially means, the third assumption is that, let's say, n moles of liquid is being vaporized. That means n mole of vapor will also be condensed. So these are three of the main assumptions in a McCabe-Thiele method. So what follows this is just a lot of mass balances and component balances. So fine. Another important thing is that the top part of the distillation is called the rectifying section. It can also be called as enriching section. And the bottom part of the distillation column is called as the stripping section. Fine. So you based on these mass balances, you will have a lot of derivations um, and it will lead to a lot of general equations. So there are two such equations. So one is the general equation for the rectifying or the enriching session. So this comes from the condenser balance. So by condenser balance, we had V is equal to L plus D. And this is and when we do the component balance, we can write Vy is equal to Lx plus dxd. So we just have to solve these two equations. So here what happens is this V is equal to L plus D. We can just substitute this V is equal to L plus D into the second equation, and by rearranging it we will get the general equation for the enriching section or the rectifying section as Y is equal to L by V into X plus D by V into XD. Fine. Now let's take a condenser like this. So I mentioned that a fraction of this goes back into the distillation system as a liquid. So there is a new term here called as reflux ratio. And this reflux ratio is nothing but the ratio of liquid that goes inside the distillation column, which is L, by the uh, distillate that is going out of the distillation column. So this can be represented as R. So now in this general equation, we have Y is equal to L by V plus D by V into XD. So we can rewrite this equation in terms of the reflux ratio as R by r plus 1 x plus xd by r plus 1. So these two are the most commonly used equations, the general equations for the rectifying or the enriching section. Now in a similar way, by using the reboiler balance, we can write the general equation for stripping section. So the general equation for stripping section is also very similar to this. Y is equal to L bar by V bar L bar by V bar into X minus W by V bar into XW. So this is the general equation for the stripping section. And this we will get by using the mass balance and the component balance from the stripping, the reboiler balance. Yeah. Okay. So in your classes, what you usually do is you use these operating line equations, and you usually try to find the number of trays by a graphical method using McCabe-Thiele. So this graphical method, it's nothing like we can take our x-axis and y-axis, which represents the uh, mole fractions, and we have our 45-degree line, and then we have our equilibrium curve. Okay, now so let's say xf is our feed, and this point xd represents our distillate, and this point xw represents the mole fraction of the more volatile component in the residue. So how you usually do graphically is that we use this equation y is equal to r by r plus 1 x plus xd by r plus 1 is the equation for the rectifying section, and this line is represented by this. So this line is of the form y is equal to mx plus c basically. So where m is the slope and c is the constant which is the intercept. So this intercept is basically xd by r plus 1, and this slope is basically r by r plus 1. Now in a similar way, you will also be able to find the operating line for stripping section using the formula y is equal to L bar by V bar to x minus um, what was the formula? Yeah, W by V bar into XW. So yeah, you can use this to find the stripping section. The operating line will go something like this. And what you usually do is you connect the operating lines of the enriching section and the stripping section with the equilibrium line like this. And basically what you do is you calculate the number of these steps. So let's say this is 1, this is 2, this is 3, this is 4, and this is 5. The number of steps that is required to cross from xd to xw. So that let's say as n is equal to 5 is the number of ideal stages or trays required in a distillation column. So this is one way that you do graphically for the McCabe-Thiele method. So yeah, so these are just some of the basic concepts of McCabe-Thiele method. Now let's okay. All right. So there is one more term you need to be familiarized with while proceeding for the um, numerical problems, which is the feed line or the Q line. Right. So there is one term which is called as Q, which is nothing but the fraction of liquid in the feed. So the feed that you put inside the distillation column can be of 5 different types. It could be subcooled liquid, it could be saturated liquid, then it could be a mixture of both liquid and vapor. So liquid vapor mixture. Then it could be saturated vapor, and it can also be superheated vapor. Fine. So this Q basically tells us how much of your feed is liquid. So when your feed is subcooled liquid, this Q will be greater than 1. And when your feed is saturated liquid, this Q will be 1. And when your feed is a liquid vapor mixture, it will be between 0 and 1. And when your feed is saturated vapor, Q will be 0. And for superheated vapor, it will be less than 0. So this is something called as the Q line or the feed line. So this is also important when it comes to solving numerical questions. So if Q is the fraction of liquid in the feed, then normally 1 minus Q can be the fraction of vapor in your feed. Yeah. So this Q line will represent it graphically like this. So we had the operating lines of the enriching section and the stripping section like this. This Q line will originate from XF and it will go like this normally. And this Q line can be represented by using the balances around the feed tray as Y is equal to Q by Q minus 1 into X minus XF by Q minus 1. So this is the general equation or the equation representing this Q line. Yeah, so these are some of the basics and mainly the basic general equations that you need to remember while solving problems from distillation. So let's get to today's questions for distillation. Okay, so let's go with the 2018 question. So before we proceed, is the basic concepts of this distillation, is it clear to everyone? Like, do you have any particular things that you want me to explain in mind, or like Do you have any doubts from the things that we just looked into just now? Like feel free to interrupt me at any time. Like I'm more than happy to help. Is this fine or like shall we proceed? Can anyone respond? Okay, I assume things are fine. Fine. So let's get into this question. So this is a question from 2018 GATE Chemical Engineering. So binary distillation column is designed by McCabe-Thiele method to get a distillate mole fraction of zero point 0.9. The enriching section operating line has an intercept with the y-axis at 0.3 mole fraction. The ratio of liquid to vapor molar ratio in the enriching section is dash rounded off to 3 decimal places. So this you can have the reference NPTEL lecture series for this concept from lecture 3 week 9, number of trays by McCabe and Thiele for distillation, mass transfer operations 1 by Professor B. Mandal, Department of Chemical Engineering, IIT Guwahati. So these videos are available for free in NPTEL website. So you can but it's suggested that you make use of this opportunities to get the concepts more clear. So let's just write the things that they have given to us, the data that they have given to us. They have given that XD, which is the mole fraction of the more volatile component in the distillate, as 0.9. And they have also given us that the slope or the intercept of the enriching operating line with the y-axis is 0.3. So we just saw how this enriching operating line intercepts the y-axis and how that y-axis is related to the general equation of the enriching section. So that is 0.3. So for an enriching section, we just looked at the general equation y is equal to r by r plus 1 x plus xd by r plus 1. So that intercept 0.3 is basically the intercept which is available from the general equations. So here this 0.3 is equal to xd by r plus 1. Yeah, and then the slope is also r by r plus 1. And the other form of this equation will show us that the slope is also equal to L by V. So basically what we have to find here is L by V, and it is equal to R by R plus 1, where R is the reflex ratio. So now all we have to do is substitute the values that we have here. So we have the value for XD, which is 0.9. We have the value for Y and X. Yeah, so we have XD by R plus 1 is equal to 0.3. So just substitute the values here. XD by R plus 1, XD is 0.9, and we have 0.9 by R plus 1 is equal to 0.3, and we can solve this equation to find R, which is 2. So L by V is equal to R by R plus 1. Yeah. So which is basically equal to 2 by 2 plus 1, or by 2 by 3, and this roughly comes to 0.667. So this is a straightforward question that we can solve using the concepts that we learned while doing the McCabe-Thiele graphically. Is this clear? Okay, let's move on to other problems. Fine. So this is a question from 2017 GATE. The composition of vapor entering a tray in a distillation column is 0.47. The average composition of the vapor leaving the tray is 0.52. All the compositions are expressed in mole fractions of the more volatile component. The Murphree efficiency based on the vapor phase rounded off to the nearest integer is %. So you can also find the NPTEL lecture series for this in the NPTEL website done by Professor B. Mandal from IIT Guwahati. So yeah, there are a few efficiencies which we can measure. Basically the efficiency of the tray or the efficiency of mass transfer that occurs in a distillation column. And one such efficiency is the Murphree efficiency. So by definition, let's take a tray and let's say it's the nth tray. So there will be liquid coming in, liquid and vapor coming in and going out. So let's say Ln minus 1 is the liquid that is coming from n minus 1 tray, and Ln is the liquid that is going out from the nth tray. And you will have vapor also as Vn plus 1 coming in and Vn going out of the nth tray. Their corresponding compositions can be represented as Yn for Vn, Yn plus 1 for Vn plus 1, Xn and Xn minus 1 for the liquid. Now this is for a real case. Now there is a, when you do it for an ideal case or the ideal stage, this Yn and this Xn of Vn and Ln will be in equilibrium. So we can represent that as Yn star and Xn star. So in ideal stages, the products leaving the nth tray are in equilibrium. So Xn can be represented as Xn star and Yn can be represented as Yn star in ideal case. So by definition, the Murphree efficiency is nothing but the change in composition in a real case by change in composition in an ideal case. So Murphree efficiency Em is equal to change in composition for a real tray or stage by change in composition for an ideal stage or tray. And if you want to represent it as in percent into 100%. So for a real stage, the change in composition, or here we want it in the terms of vapor composition. So change in vapor composition for a real stage is equal to Yn minus Yn plus 1. And similarly, when it comes to the ideal case, change in vapor composition for an ideal stage. So here, yeah, the change in vapor composition for ideal stage is equal to Yn star minus Yn plus 1. So yeah, the Murphree efficiency in terms of vapor phase composition is nothing but the change in composition for real case by change in composition for an ideal stage, which is basically Yn minus yn plus 1 by yn star minus yn plus 1 into 100%. So this is the Murphree efficiency's general equation in terms of vapor phase composition. Now we can also write this similarly in liquid phase composition as xn minus 1 minus xn by xn minus 1 minus xn star into 100%, and this is in terms of the liquid phase composition. So here also the concept is same. The Murphree efficiency is equal to change in composition, the liquid composition for a real stage by change in the liquid composition for the ideal stage. So now we have been given a few data here. So here yn is given as 0.53, yn plus 1 is given as 0.47, and yn star is given as 0.52. So we just have to substitute these values in the vapor phase equation, and we can find the Murphree efficiency by just direct substitution. So Murphree efficiency Em is equal to 0.53 minus 0.47 by 0.52 minus 0.47, and this will come to 120%. Is this clear? Okay. Fine, let's move on. Okay. So this is again a distillation question which was asked in GATE 2015. So a binary feed consisting of 25 mole percent liquid and 75 mole percent vapor is separated in a staged distillation column. The mole fraction of the more volatile component in the distillate product is 0.95. The molar flow rate of the distillate is 50% of the feed flow rate, and the McCabe-Thiele method can be used to analyze the column. The Q line intersects the operating line of the enriching section at 0.35 and 0.5 on the XY diagram. The slope of the stripping section operating line up to 1 decimal place is dash. So we have to find the slope of the stripping section, which is basically L bar by V bar. So let's see how to proceed with this question. So let's draw our distillation column. So we have the feed F with the composition XF. We have the distillate D with its composition XD, and we have the residue W with its composition W. So it is given that the feed is 25% liquid. That means Q is equal to 0.25, and the mole fraction of the distillate is also given as 0.95, and the molar flow rate of the feed is twice that of the distillate. So that means F is equal to 2D. Okay. So they have also given us that the operating line of the enriching section intersects the Q line at 0.35 and 0.5. That means at the feed tray, the X is equal to 0.35 and Y is equal to 0.5. So let's write the general equation for the enriching section. So Y is equal to R by R plus 1 into X plus XD by R plus 1. So we have the values for XD, we have the values for X and Y from the intersection. Just have to substitute it to find R. So 0.5 is equal to R by R plus 1 into 0.35 plus 0.95 by R plus 1. So this is just direct substitution and solving this equation to find R. And by solving this equation, we find that R is equal to 3. So R, which is the reflex ratio, is equal to L by D, and we have L by D is equal to 3. So just rearranging it, we can write it as L is equal to 3D. Now let's take a condenser balance. So we have the distillate D, the liquid that is going inside back as L, and V is the vapor, and the condenser balance V is equal to L plus D. So here we already have L is equal to 3D. So we just have to substitute V is equal to 3D plus D, or V is equal to L plus D. Substitute for L as 3D, and we get V is equal to 3D plus D, which is 4D. Yeah. So feed is 25% liquid. That means 75% vapor. So we have Q is equal to 0.25. So let's take a feed tray balance. So we have the feed incoming, which is F, the liquid incoming and outgoing as L and L bar, and V are V and B bar as the vapor that is coming in and going out. So from these equations, we can write the equation. Um, yeah. So we can write an equation using L bar, L and Q as L bar is equal to L plus QF, and V bar is equal to V minus 1 minus Q into F. So this equation is this L bar equation. Just a second, sorry for the interruption. I lost my. Okay. Okay. Sorry for that. Okay. So L bar is equal to L plus QF. So what this means is L bar, which is the liquid that is going out of the feed tray, is equal to L, which is the liquid that is coming into the feed tray, plus Q into F, which is the fraction of liquid that is available in the feed tray. And similarly, we can write a balance for this V bar as well. So V bar, which is the vapor that is entering the feed tray, is equal to V, which is the vapor that is exiting the feed tray, minus 1 minus the fraction of vapor that is available in the feed. Okay. Fine. So just substitute the values. We have L is equal to 3D. So L bar will be, and we also have the value for F, which is 2D. So just write this equation L bar in terms of D. So L bar will be, yeah, L bar will be 3D plus 0.25 into F, and F is 2D. So L bar is equal to 3D plus 0.25 into 2D, and we'll get L bar is equal to 3.5D. Similarly, we can also write V is equal to 4D from the condenser balance. So we can get an equation for V bar as well in terms of D as 0.25D. Now slope of the stripping section is equal to L bar by V bar. So this is what we need to find here, L bar by V bar, and this will be equal to 3.5D by 2.5D, and we can cancel out these terms and we'll get the final answer as 3.5 by 2.5, which is 1.4. Yeah. So yeah, this is the ratio of the liquid to molar flow rate of the liquid to the vapor phase in the stripping section, which is equal to the slope of the stripping section. So these are like some of the questions that is asked in the previous gate years, and you can see most of these questions rely on mass balance of the distillation column, and the condenser and the reboiler as well, and it depends on the general equation of these operating lines as well. So these are some of the concepts you need to learn for preparing for gate, especially in mass transfer and distillation. Any doubts on how we proceeded with this, how we got the answer? Okay, fine. That's about it for today. So we looked at, just to summarize what we did today, we looked at few of the concepts with regards to distillation and relative volatility. We looked at how we can graphically represent the McCabe-Thiele method, the operating lines for the enriching and the stripping section in graphical form, and how to find the number of trays in graphical way. And we also looked at three questions from previous year gate, which relied mainly on the general equations for these operating lines. So yeah, that's about it for today. And yeah, thank you for joining. And if anyone has any doubt, please you can unmute yourself and speak or type in the chat box. It's up to you. So yeah, that's about it for today. And I hope this section was somewhat useful and you were able to get something from out of this section. And yeah, thank you and see you all next Monday.